So previously we had talked about Pascal's triangle, and we had noticed that there's this neat property that happens with Pascal's triangle, namely that we had this summing of the rows, and each row would sum to a power of 2. I would like to be able to try to answer that question of what's going on there. Now, to answer that one, including other questions, I'm going to address something from algebra, referred to as the binomial theorem. So let's talk about the binomial theorem. So we're going to talk a little bit about algebra first, and then we'll kind of eventually work our way back to answering that question about how do we know that the sum of each row of Pascal's triangle is indeed a power of 2. So just some background. A common form in algebra is the binomial. So you might ask, Dan, what the heck is a binomial? So let's talk about that. So a binomial is a sum of 2 terms, usually numbers. For us, this will be a plus b, where a and b are numbers. So I'm going to start off by exploring a question about powers of binomials. So meaning how many times you multiply a binomial. I want to explore this question and see if we can pull out from it some combinatorial structure that's happening underneath the hood. So that's going to be our main goal. So for any non-negative integer n, what is a plus b to the power of n? So let's explore this for some values of n. I'm hoping that we can talk a little bit about how you can figure out which one is and what it isn't. And we're going to re-explore some topics you may have seen possibly before. So first, let's consider when n is equal to 0. Let's start off with that. Well, a plus b to the power of 0. You know, anything that you add where it's a plus b and these are numbers, you raise that to a power of 0. What is that? Well, that's just 1, right? We have n is equal to 1. Well, a plus b to the power of 1. Well, that's just simply a plus b, right? That's just the thing. A plus b. How about n is equal to 2? Now, I want to re-explore something. You may or may not have heard of this before. You may have learned it in grade school, possibly. It's a helpful way of remembering how to multiply binomials. So just think of this first as an aside, and then we'll work to answering this question. So first, in grade school, maybe, maybe not. I'll say maybe, question mark. You may have learned a rule called the FOIL method. So if you're wondering what the FOIL method is, what it stands for is as follows. So it means first, outer or outside, depends on who you talk to. Inner, inside, and the last one's last. So this gives you a simple way of remembering how to multiply binomials. But honestly, I'm going to show you that you don't need to remember such silly rules like this, although they do work. But You don't have to remember it like that. It's actually a much more general way of just viewing the same thing. It's just meant to be a simple way of remembering what you're doing. But I find a lot of time when they teach you this, they don't tell you why it's the case. So let's talk about this. For multiplying binomials. And is applied as follows. So suppose that I have numbers a1, b1, a2, and b2. So if I give you a1 plus b1 times a2 plus b2, you may have learned this to go like this. You multiply the first of each, that's the f, a1, a2, so this is the first, that's your f right there. Then you have a1, so it says now you're going to go outer, so we have a1 times a b2. There's your O part. Then next, you have the inner part. You have b1, a2. You take the two inner terms, b1, a2. So this is the I part. And the last, we just take the last two like this. b1, b2. So there's your L right there. So that's how you would apply using FOIL. Now, you might say, Dan, why would this work? And why does this, why? Like this is how I learned how to multiply binomials. We never really were ever explained by our teacher why this works. So let me just show you, just for context, what's actually going on. Or at least this is one way of deriving it. So really, actually what's happening is we're actually taking advantage of distributive properties of numbers over multiplication. That's actually what's happening. At least that's one explanation I could provide for you. So really, so what's actually happening? So what's actually happening? So let's revisit really what's going on here. So what's actually happening? Well, we are multiplying each term in the first pair, so the binomial in the first binomial, in the first pair, or binomial, I'll say just binomial to keep it simple, first binomial, against each term in the second binomial. Each term in the second binomial. And adding these products. So just to really explain or hammer this in where the heck this came from, let me do it with just A and B. Just A and B, because this is more what we're interested in. So for example, if A1 equals A2 is equal to A, and B1 is equal to B2 is equal to B, then if I give you A plus B times A plus B, I want you to look at this as just one variable, okay? I want you to just look at it just as one variable. So imagine this was just like X or something. So imagine this is just to make it look a little scary, well, a little less scary, sorry. Just imagine this is just like X. What would you do in that scenario? You would distribute X across A plus B, right? So you would have XA plus XB, right? So the same thing happens here. There's no black magic happening. So I'm just distributing over one of the binomials. That's all that's actually happening. So this is a times this. So I take a times this, b times this. I'm distributing a plus b, this binomial, over each one of these terms. So I have a times a plus b times a plus b, right? That's all that's happening. I take this, multiply it by a plus b. Take b, multiply it by a plus b, right? That's all that's happening. There's nothing to memorize here. It's just remember, the multiplication is distributive like this. So now, what do you end up with? A. So this is a times a is a. Then I have a times b. So I have a, b, plus b times a, plus b times b. Look, there's your FOIL right there. Do you see it now? So if you're not seeing it right away, go back to the other example. Just put A1, A2, B1, B2 in, and just go through the same exercise we just did here. So the point, I'm just going to keep it explicitly like this. It's going to be helpful for us to exploit or discover the underlying structure of what's happening when we multiply binomials. Is first, notice that I had multiplied a plus b twice. That's the first thing I want you to notice. So notice that each one of these has either an a or a b, and there's two of them in each one. Each of these products has two variables, right? A or b, right? So now, if we understand how that works, let's try n is equal to 3. So let's do n is equal to 3. So all I'm going to do is I'm going to use n is equal to 2 to help us do n is equal to 3. So let us expand on the previous case. So if I have a plus b cubed, I have a plus b cubed. Well, what is this? Well, if I know the answer to a plus b squared, which is this, how do I get a plus b cubed? I just multiply it by a plus b. And you'll notice that since I have the answer to a plus b squared, it's sitting right here. What can I do with this? Do the same exact thing. I distribute across each one of the terms that is the result of a plus b squared. I multiply each one of these with this binomial. So this is the same as me writing AA plus AB plus BA plus BB times A plus B. Then I'm going to now distribute it across each one of the terms, the resulting products. So that's right, B plus A. I want to keep it simple. A plus B. Then I got the third term, BA times A plus B. And I have BB times A plus B. Next. Now I gotta multiply this all out, okay? So let's do this. So I have AAA, right? AAA. Then I have the other possibility. So thinking about it as an either or is rather helpful for us in this discussion. So I have AAA, then I have AAB plus ABA plus ABB. Then I have BAA. That BAB plus BBA plus BBB. And now if you simplify this, that will give you, so if you take all the like terms and you lump it all together, you'll end up with an answer for n is equal to 3. But I'm going to explicitly keep them in this form, okay? Just to make it easier for you to see what's happening. So again, notice n is equal to 3. Each one of our terms, each resulting product, has 3 variables in it. And each one is either an A or a B. So take notice that I can uniquely determine each one of these. So notice that I can either pick an A or a B. And each one of them has either an A or a B in the first spot, an A or B in the second spot, and an A or a B in the third spot. I'll let you check that. So let's talk about what a factor is. So the number of factors. So I'm going to use this term factors. You might know of this term from factoring. Number of factors of a binomial is the number of binomials rewrite it in a write out in a product. So the number of factors of a binomial is the number of binomials we write out in a product. So for example, if I did a plus b to the power of 4, it has 4 factors. We have a plus b, a plus b, a plus b, and a plus b. We would call this factor 1, or the first factor. We can call this factor 2, or the second factor. This could be factor 3. And this is factor 4, or the fourth factor. So, as I mentioned to you, we can completely determine any one term that appears in the expansion of this product, just like in our n is equal to 3 case. So we can completely, so this is going to be rather important for us. So please take note of this. We can completely determine any one term that appears in the expansion of products. So remember, we end up with just we're summing a bunch of products, right? That appears in the expansion of products for, suppose if we consider n is equal to 4, we would have a plus b to the power of 4, just as an example. Through selecting either A or B for each A or B from each factor. So what I'm saying is, if I were to give you A, that if I pick this A from the first factor, and I pick an A from the second factor, and I pick an A from the third factor, and I pick A from the fourth factor, this will exist in the list of terms, the products that would appear in the sum that equals A plus B to the power 4. That's what I'm saying to you. So let me just give you an example. So just as an example, if I consider a plus b to the power 4, well, this is just like I did before, is a plus b cubed times a plus b. Well, I already know the answer to this. So this is just AAA plus AAB plus ABA plus ABB plus BAA plus BAB plus BBA plus BBB. I'm trying to do that without breathing. It takes some practice, okay? And then I multiply this by a plus b. So remember, this is the product of 3 factors, right? So this is all the products with 3 factors. Then all we're doing is we're appending an A or B. That's the kind of combinatorial mindset I really want you to look at when we're looking at this. Is I have the result of 3 factors being multiplied out, and then I append either an A or B. So you can even look at this, they look sort of like strings when I could just append an A or a B. But remember, algebra has all sorts of fun other properties, so we got to be careful when we say things like that. So this is just A plus B plus A. So remember, all I'm doing is I'm going through each one of these terms. I write an A after it, or I write a B. So I go through each one of these. I'm just A. Then the next one would be B. So now I've considered B. So now let's do ABA plus B, right? And then next we've got, so far, it makes it a little easier to help us maybe keep track of these. So we got ABA, I got ABB next. So we got ABBA, got some ABBA. And then we got ABBB. Now we got all the ones with B's. We've got BAA plus BAAB plus BABA. We got Baba. I think I got Grandma. Got BABB plus B. Let's go with B. I think it's BB. Yeah, because the next one is BBA. So we got BBAA plus BBAB, right? And then last, we have the last two. Then we have BBBA plus BBBB. So now, do you notice that I can just simply pick a selection of A's or B's? So either A or B. You can imagine each factor like a position. If you think about it like a position, this all clicks really nicely. So if I pick an A, then a B, then a B, you'll see it's in this list of terms. So each of these products actually can be completely determined by the choices of either A or B for each factor. That's the claim. And you can see it right here, right? You can do this with any one of these. So just like we see with the previous ones, you can keep doing this. Like, I encourage you, if you're not convinced by this, try A plus B to the 5. Now, what I'm going to do next is I'm going to take this term, this collection of terms right here, these resulting products, I'm going to now notice something. Because algebra has more properties than just saying, oh, look, I can write these out nicely, right? You know, you can actually group like terms, right? We can take terms that are similar. We can commute elements in products. We can take like terms, so we can associate them differently. So why don't we do that now? So I'm going to take what I have, that list over there. Now I'm going to simplify it down, and we'll see if we see anything interesting pop up. And please take note of the fact that in this example, n is equal to 4. So I want you to think back, just think back to Pascal's triangle. If you could think about Pascal's triangle. So notice by associative and commutative laws, laws of algebra, some terms are the same. They're like terms. So we're going to group them together. And I can actually group them into 5 distinct categories. So the first category is those that have 4 A's in them and no B's. They always look like this. So they have 4 A's in them, no B's. So there's one of these. So there's one many of those. The next one is when I have 3 A's and 1 B. So remember, like I said, I can rearrange some of these. So for example, notice that I have 2 B's in this one and 2 A's. This one also has 2 B's and 2 A's in it. So these are actually both the same. They have the same result, algebraically speaking. So let me just list out these for when I have 3 A's and 1 B. So that was the case when I had 2 A's and 2 B's. That'll appear actually in a list of those that I'll get to in case 3. So I'll have AA, AB, then I have AA, BA, then I have ABAA, and then I have BAAA. So there's 4 of these. There's 4 many of those. Next, let's consider when we have 2 A's, 2 B's. Well, we're going to have 2 of the ones I just mentioned. We'll have AA, BB. We're going to have AB, AB, ABBA. So I'm just grabbing all the ones with 2 A's and 2 B's in it, and I'm just listing them out for you so that way you can see how many of them there are. So I have ABBA, then I have BAAB, then I have BABA, got the babushka, and BBAA. So that has 6 many, right? There's 6 there. 1, 2, 3, 4, 5, 6. There's 6 of them. So next, let's boogie on here. Let's do case 4. So now I have 2 1's, 3 B's. So I have A, B, 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 A, B, 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 A, B. And then I lastly have B, 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 A. So notice I've just simply considered each case where I just put A in different spots among the 4 positions. You'll notice that actually when I write it out like this, it should remind you a lot if I was asking how many strings there are that have that many symbols in those spots. So it should remind you a lot of the earlier counting principles that we're looking at, except we're mapping them onto positions. So in those exercises, that exactly is what we did. Then lastly, we have it where we have, wait, oh, that should be 1. For some reason I wrote 2 there. I didn't have Miss Kitty or anybody to tell me, don't do that, Dad. You've gone too far, you put a 2 there. It's too late now. Now I fixed it though. All that Miss Kitty, I don't know where she's at. So so let's consider when we have no A's, 4 B's. So this is easy, it's just 4 B's like this. Well, there's 1 of those, right? So now what I want to do is I know how many of these are each. 1, 4, 6, 4, 1. That should look oddly suspicious to you, right? I want you to think to the 4th row. So when n is equal to 4, actually specifically I want you to think of when n is equal to 4 in Pascal's triangle. What were the binomial coefficients that you read in that row? 1, 4, 6, 4, 1. When n is equal to 4. So I should be careful. Depends on where you count the rows are from. It's when n is equal to 4. So when we combine like terms, then a plus b to the power of 4 is equal to 4 choose 0, a to the power of 4, b to the power of 0, plus 4 choose 1, times a to the power of 3, b to the power of 1, plus 4 choose 2, a squared, b squared, plus 4 choose 3, a to the power of 1, b to the power of 3, and lastly we have 4 choose 4 of a to the power of 0, b to the power of 4. Well, what is that? What is that? No period, no period. I've got to simplify it further. Well, what is that? Well, let's see. Well, this is just, remember, that's just 1, so it's just a to the power of 4, right? So I'm going to simplify this. Got 4 times a cubed times b plus 6 times a squared b squared plus 4ab, so 4ab cubed, where b is cubed specifically, plus b to the power of 4. So all I've done is I have, notice the coefficients, they match that row of Pascal's triangle. So there's your binomial coefficients, and you end up with this form right here. So for example, I encourage you to try going through the same exercise we did here with n is equal to 3 or n is equal to 2, and see if you could come up with the binomials, specifically when n is equal to 2, see if you end up with exactly what you would anticipate if you expanded the, like if you took those terms and you simplified it. Do you see if it matches up exactly with what you'd get from, say, the FOIL method? So you notice that this actually gives you a generalized pattern if you think more about it. So the idea more generally is the binomial theorem. We're going to prove the binomial theorem, which characterizes a row, like you can see that hiding in it is a row of Pascal's triangle. So we're going to use that fact after to actually answer the question about why the sum of each row of Pascal's triangle is a power of 2. Once we have the binomial theorem, we'll be able to answer that. So after this, I will talk about that. So I'll specifically talk about it after we use the theorem, so you can get used to it. It's a valuable theorem to be aware of. If you want to remember the form of what a binomial would be, this theorem is your best friend. For any a, b, which are real numbers, I'll let us use real numbers here, and n, which is going to be a non-negative integer. I must stress that there do exist other forms of this theorem, but ours, we're just going to presume the exponent is a non-negative integer, so it's allowed to be 0 or above. What binomial theorem says is that a plus b to the power of n is the sum from k is equal to 0 to n of n choose k times a to the power of n minus k multiplied by b to the power of k. So this is the binomial theorem. So there's a few things I really want to point out is notice that how I showed you from case by case, it alternates on, so this goes down, this one goes up on k, and each one has the binomial coefficient as we discussed previously. So if you're looking at this and like, oh, what the heck does that mean? Try it with n is equal to 2 and see if it matches exactly what you'd expect a binomial to be if I took a plus b times a plus b and simplified. So we're going to do this proof, we're going to break it into 2 cases just because the argument is easier when I can presume that n is greater than 0. So I'm going to break it into 2 cases. The first case is really easy. So I'm just going to prove the claim directly for n is equal to 0. Then when n is equal to 1, 2, 3, or higher, I'm going to use a combinatorial argument. I must stress that if you don't like this argument, you're welcome to prove it algebraically, or within, I believe the standard proof for this is actually induction, actually. Yeah, it's induction, sorry. Yeah, you can use induction if you don't like this combinatorial argument. So, here we go. So, we consider 2 cases. First, when n is equal to 0, and when n is greater than 0. So the first case, we're just going to assume n is equal to 0, and we're just going to prove it directly. And of course, these are all values of n. And in each one of the cases, it won't matter. We have to argue regardless of A or B that the claim is true. So when n is equal to 0, the left-hand side, what's the left-hand side say when it's 0? Well, we already established it's just 1, right? The left-hand side is a plus b to the power of 0, which is equal to 1. Regardless of a or b, so whatever a and b's values might be, when n is equal to 0, the right-hand side is as follows. So let's take a look at what the right-hand side says. The right-hand side, we're going to plug in when n is equal to 0. The right-hand side is as follows. The sum from k is equal to 0 to 0 of 0 choose k times a to the power of 0 minus k times b to the power of k. Remember, I just put 0 everywhere where n was. So then, remember, sum from 0 to 0, well, I'm just going to have a single term in here. It's just 0 choose 0 times a to the power of 0, b to the power of 0, right? Because k only is allowed to be the value 0. Well, 0 choose 0 is just 1, right? A to the 0 is 1. B to the 0 is 1. So this is all 1. So the claim holds. So the claim holds for n is equal to 0, right? So it holds for n is equal to 0. Now we got to consider when n is greater than 0. So our second case is when n is greater than 0. So we're going to start by considering the left-hand side and see what that means based on a discussion about factors. So consider the left-hand side, which is a plus b written exactly n times, right? It looks like this. A plus b to the power of n is equal to a plus b, and so on, a plus b. But this is written n times. Now, when we take this, as we discussed previously, we can take the resultant of this and we result with an expansion with a whole bunch of products. What did we say about those products? How many variables appeared in each one of the products? Well, it depends on this, right? N. So for example, when n was 3, then each one of the products had 3 variables in it, either an A or a B, right? So let's just observe this. So now, so that over there, this can be expanded. This can be expanded into products. Into products. Each with n, so I'll say with, I'll just write without fully, with n variables. With n variables. So to be clear, this is 1 from each factor. So 1 from each one of the factors. So remember how we determined each one of the resulting products? Had 1 from A or B. We grab 1 from each factor. 1 from each factor. where each variable is either A or B. Is either A or B, right? Now there's n factors, right? So we can say something a little better than just what we have down over there. As there are n factors, observe each of the products has the following form. Has the form as follows. So do you know how I went through and I increased A and then I decreased B? Like I kind of alternated them based on K? We can do that more generally. Has the form A to the n minus k, B to the k, which is equal to as follows. A times all the way up to some number of A's. B times some number of B's. How many of these are there? Well, each one of these is grabbed from some factor, right? So how many factors do these A's come from? There's n minus k factors that these come from. And then over here, we have k factors that we picked B's in. That's what this all this is saying, right? So all of the ones that have this form look like this, where it has n minus k factors and k factors if you were to just commute them, right? So you can rearrange them so they look like this. The question is how many of them there are, right? But the point is that you could do this over each of the k values, right? So each of them has this form for some k, which is, you can take on the value 0, 1, 2, all the way up to n, right? So please remember that each of these products has k of its n positions assigned the variable b. Assign the variable b. What happens with all the other ones then? So if I have n positions, so you imagine I have n of them, some of them go in b's, right? So what goes in the blanks? A's. They all get filled up with A's by default. Well, if k of them are b's, then n minus k of them, as you might suggest from this, each of these products that would take on a form like this, well, you can think of each one of these like a group of these products, right? And I want to know how many of them there are. So that's what we're going for next. So the remaining n minus k positions contain A, right? Now, let's ask a question now. Based on what we just described, if I look at each one of these groups of products, so I have the ones with k is equal to 0. I have the one where the k's are equal to 1, the ones where k is 2, k is 3, all the way up to k is n, right? So I want to know how many there are for each one. So for each k is equal to 0, 1, 2, all the way up to n, the number of products that contain B exactly k times is the number of ways to choose k positions from the n positions, right, to place variable b. To place variable b, right? What does that equal? If I have n positions, I select how many of them? K many positions to put b's in. So remember, think of it like a set where each one of the elements in the set is a position. And I pick k of them. So what is it? It's n choose k, right? Which equals n choose k. Now, very last step of this. Last step. Now we know how many for a particular value of k. So now we just got to consider all of them over k. All of the products. So to consider all the products, we have to sum over all values of k. Right? That's what a plus b to the power of n is, right? That's what the resulting expansion will equal. Therefore, by summing over k is equal to 0, 1, 2, all the way up to n, what does that mean? Well, it's a plus b is power of n, right? Remember, that's what we established already, right? Is that we can break it up into the factors, right? There's n of them. Then we realized, okay, each one of them has like a form that it takes on based on associative and commutative laws of algebra, right? Then we wanted to know how many times that appears. And we realized for each k, it's n choose k. So if I write this out carefully, in a much more fancy way, before I get to the fanciest way, the way that I want to prove the claim, let me write it out group by group. So it would be n choose 0 because this one has no b's in it, right? This one has one b in it. This one will have, next one will have two b's and so on. I'll go up to n choose k, which that would be a, or I have n minus k many a's, and then b, I have k b's, all the way up to n choose n. Sorry, I need to have some dots in here. There's more terms in between here. There's more terms in between here. I need the dot, dot, dot. It's very important. Plus, where I have no a's and all b's. But what's this? Let me write it out using summations. So let me use some notation. So I'm varying k from 0 up to n. So k is equal to 0 up to n. This is n choose k times, the general term of this would look like this. N minus k times b to the k. But what is that? That's exactly what we were trying to prove, right? Which we sought to prove. Which we sought to prove. And that completes the proof of the binomial theorem. So just remember, the big idea here is that we identify that this has that expansion, or it has, each one has each of the products, so it goes into an expansion of products. Then we know that each one of them actually has a specific form, and we wanted to know how many of them are there. So to consider all the products, I had to vary it over all possible values of k. And that's how I get the right-hand side. And then I simplified. Or refined it, I guess. The best way to put it. But that's the proof for the binomial theorem.